Hello friends, I welcome you to my YouTube channel Back PM. So in today's video we will solve a numerical problem which is based on the columns. So in previous video we have seen how to derive Euler formula and what are the columns and what are the variables and the conditions. So in this video we will solve this numerical problem. If you want to start from the basic, then I request you to please go through the playlist. Okay, so a simply supported beam of length 4 meter is, so let's note down a simply supported beam. What is the simply supported beam? A beam is like this, okay, and one end is hinged or pin joint and one end is roller support. Okay, this is simply supported beam, has a length of 4 meter. So this is 4 meter. Is subjected to uniformly distributed load of, so this is uniformly distributed load. Okay, this is W is equal to 30 kilonewton per meter over the whole span and deflects 15 mm at the center. So under this load the beam will deflect like this, and this maximum deflection at center is 15 mm. Okay, so this is the given in the question. Determine the crippling load when this beam is used at the column with the following condition. So there are two conditions: one end is fixed, another end is hinged, and both end the ends pin, pin jointed. Okay, so both of the pin joints or hinge joint. Okay, so why this is given as beam, then it is asking for column. So what is the difference between beam and column? Beam is usually loaded like this, perpendicular to its length. Okay, transverse loading. But in case of column is beam is mostly horizontal and column is the vertical component. Okay, column will be like this. So if we rotate this beam 90 degree and if we load it like this axially, then it will become a column. Okay, so this beam is given to us so that we can find EI. As we know that Euler's formula P crippling or P buckling is pi square EI upon L effective square. Okay, so this is Euler formula, and in this case if we see carefully, then we have not been given the value of E and I, which are constants. Okay, so cross section of beam is not known, so we cannot find the value of I, and the value of E is also not given. Okay, value of L is given. This is 4 meter normal length, so we have to find effective length, but value of EI is not known. So from this beam we can find the value of EI. How? So if you see in any book or if you remember, then you will know that maximum deflection delta max for a beam is what? Simply supported beam which is uniformly loaded throughout the cross section, throughout the length or span. It will be equal to 5 divided by 384 into W L to the power 4 divided by EI. Okay, so this is formula for the maximum deflection of this beam. You can also derive it, but if you derive it, then it will take a lot of time. In the same channel we have derived this formula also. If you go under the deflection of beam playlist, you can find that. Okay, so we will directly use this formula so that we can do it quickly. So if we put the values here, this is deflection delta max is 15 mm, so it will be 15 into, or if we keep everything in mm, then it will be 15 is equal to 5 divided by 384 into what is W is 30 kilonewton per meter. Okay, so it is W is equal to 30 kilonewton, means 30 into 10 to the power 3 newton per meter. If we convert it to per mm, then it will become 30 divided by 1000, so it will become 30 newton per mm. So we will put at W is equal to 30 newton per mm into L is length is 4 meter. So if you keep it into mm, then it will become 4000 to the power 4 divided by EI. Okay, so from here EI will be equal to 5 divided by 384 into 30 into 4000 to the power 4 divided by 15. Okay, so from here if you will calculate it, you will get 2 by 3 into 10 to the power 13 mm Newton per Newton mm square. So this is value of E into I. Okay, so we will use this value of EI into our problems in column. Okay, so what was our problem? Determine the crippling load. So we have to find PC, crippling loads. In the it is used a column in the following condition. There are two conditions: one end fixed and other end hinged. So first condition is one end fixed and one hinged. It means column like this: one end is fixed and other end is hinged here. Okay, so in this case what will be the effective length? Effective length will be equal to, in this case effective length will be equal to L by root 2. If original length was L, then effective length will be L by root 2. We have seen in the previous videos. So Euler's formula will be equal to P is equal to pi square EI upon L square. Okay, so this is L effective. So if you put L effective, it will become pi square EI upon L effective is L by root 2 square. So it will become 2 pi square EI divided by L square. So this is formula for the first case. So if we put all the values, then we will get P crippling is equal to 2 into pi square into EI is already known to us, 2 by 3 into 10 to the power 13 divided by what is L. L is given as 4 meter, so which is 4000 mm square. So from here if you will calculate this, then you will get PC is equal to 8224.5 kilo Newton. Now what is the second case? Second case was both the ends are pin jointed. Okay, so both the ends are pin jointed, then what will be the Euler's formula? P will be pi square EI upon L square, L effective square. Here in this case L effective is equal to L, there is no difference, so it will be simply this formula. So we will put the values: P square is equal to P square EI upon L square, which is equal to pi square EI is 2 by 3 into 10 to the power 13 divided by 4000 to the square. Okay, so if we put the values, then we will get 4112.25 kilo Newton. So this is our crippling load or buckling load in case of both ends are pin jointed. So if you compare these two, then you can see that this column is 2 times stronger than this column. Okay, because one end is fixed joint. So I hope you understood this problem. If you have any doubt, then you can ask in the comment section, and if you like this video, then please share and subscribe to our channel. Thank you for watching.